Software teams face a math problem. Feature development consumes the vast majority of the sprint, leaving a tiny fraction for test authoring. QA focuses on happy paths to keep pace, while complex edge cases overflow into a secondary queue, permanently deferred by the calendar. The backlog of intended tests consistently outpaces the capacity to write them. This gap is a result of a hard limit on throughput, rather than a lack of engineering rigor. To bypass this throughput constraint, one QA team designed an orchestration pipeline inside Claude Code, using 8 distinct AI agents, strictly sequentially, to write Playwright end-to-end tests. This chart displays the direct result. Starting with a baseline of 380 happy path tests, the pipeline generated a second column of 320 complex edge case tests, bringing the suite to over 700 tests in exactly 14 days. Outputting that volume of code in 2 weeks represented an 84% reduction in test authoring time per feature ticket. The primary value here is that the system removes the time-based ceiling on what a team can choose to test. By lifting that ceiling, QA teams can move away from time-based triage and toward comprehensive risk-based coverage. A single generalized prompt cannot reliably generate complex end-to-end tests. Automation at this scale requires architectural decoupling, where specific tasks are isolated and passed sequentially. The entire multi-agent pipeline hinges on a single external dependency: high-quality JIRA tickets with explicit technical specifications. If the acceptance criteria in the ticket are vague, the generated tests will fail in practice. The system functions entirely as a context extractor, bounded by the quality of the raw material fed into it. The process begins with Agent 1, the ticket reader. It ingests the raw JIRA ticket, extracting expected inputs and success metrics, structuring a readable feature summary. That summary is handed to Agent 2, the component analyst, which pulls relevant contextual data from the Playwright inspector. Agent 2 maps the structural layout of the UI. It catalogs the interactive elements and documents the state transitions required to complete the new feature. Together, Agents 1 and 2 define what the feature is and where its components live. They build the required topographical map before a single line of test code is generated. The map is passed to Agent 3, the scenario generator. This is the node responsible for expanding the breadth of the test coverage into negative paths and boundary conditions. Because this agent operates entirely outside human time limits, it applies the exact same level of exploratory thoroughness to every ticket, regardless of its apparent priority level in the sprint. Unconstrained scenario generators present a specific risk. They will confidently invent tests for application states that do not actually exist in the codebase. To prevent this hallucination, the architecture employs an ICSR layer, instructions, context, system, and rules, to strictly govern the agent's logic. A specific rule constraint is applied here. Every scenario generated must trace directly back to the original acceptance criteria in the source ticket. If the application's behavior in an edge case is undefined by the ticket, the constraint forces the agent to explicitly flag the missing information for human review, rather than guessing the outcome. By enforcing strict ICSR rules, the system ensures the scenario generator produces a rigorously grounded suite of tests, rather than a pile of plausible but incorrect scenarios. The approved scenarios now enter the code assembly phase, passing sequentially through Agents 4, 5, and 6 to become functional Playwright scripts. Agent 4 is the scaffold writer. It constructs the basic syntax, but leaves the DOM selectors entirely blank, using placeholder comments instead. The incomplete code moves to Agent 5, the Selector Strategist. This agent references the UI map created earlier by Agent 2 to replace the blank placeholders with actual DOM targets. Agent 5 strictly enforces the engineering team's existing conventions. It prioritizes role-based locators first and only falls back to data test IDs when necessary. Finally, the test reaches Agent 6, the Assertion writer. This agent injects the specific pass or fail logic into the script. These assertions are formulated directly from expected outputs isolated by Agent 1's initial ticket summary, ensuring the code tests exactly what the product team requested. By dividing the scaffolding, selector targeting, and final assertions into 3 separate agents, each distinct component of the code adheres strictly to predefined engineering standards. The generated script is technically complete, but pushing raw automated code directly to a human reviewer creates unnecessary friction. Agent 7 operates as an internal linter for the entire file. It scans the code against a master checklist of specific testing rules. It automatically rejects CSS-based selectors and flags any hard-coded wait times, and verifies that the test names accurately describe user behavior rather than just implementation steps. The vetted script is then handed to Agent 8, the documentation writer, which generates a concise, human-readable summary to accompany the file. This documentation explicitly outlines which scenarios are successfully covered, which edge cases are specifically excluded, and where human judgment is still required. Agent 7 and 8 package the raw output into a vetted deliverable, lowering the cognitive load on the engineer who ultimately reviews the pull request. The output of this pipeline is a starting point, not an immediate comment. A human QA engineer must validate the result. In this case study, roughly 30% of the generated tests required refinement by the human engineer, typically to adjust a complex selector or improve the specificity of an assertion. The architecture also introduces direct operational expenses. Running 8 sequential agents for every single ticket consumes a non-trivial amount of API tokens. Processing 10 tickets a sprint keeps the token cost manageable, but teams operating at a volume of 50 or more tickets need to explicitly model their API expenses before adopting the structure. There is also a steep upfront labor cost. Building the required prompt engineering and tuning the rules layer for all 8 agents demands significant investment before the team sees any return in productivity. Automated pipelines of this scale depend heavily on strict cost-benefit modeling and consistent human oversight to remain viable in production. Once that architecture is tuned, the primary constraint of software testing, the lack of human hours, is no longer the binding limit on coverage. As the pipeline takes over the bulk of the drafting, the engineer's role changes. They become auditors of a rapidly expanding suite, focusing on verification rather than starting from a blank page. This matrix outlines the resulting shift in strategy. Testing moves from asking, "What can we get to this sprint?" to asking, "What actually needs testing?" Those 320 new tests generated during the case study were not randomly distributed. They clustered precisely around the known edge cases and boundary conditions that the team had historically been forced to skip. Multi-agent architectures change the rules of coverage. They provide the throughput necessary to ensure that the critical tests, once ignored by the calendar, are finally written.